Okay, this time I'm going to explain the homework programs from section 8.8 of the calculus, which is about the improper integrals. There are 20 programs to go. Number one is a review from section 8.5, which is 1/3 through 1 of y plus 4 over y times y plus 2 dy. So this is a proper fraction. So we can split the fractions into two pieces, y something and y plus 2 something. So let's use the partial decomposition technique. So this is going to be y plus 4 is equal to a times y plus 2 plus by. So let's substitute y is equal to 0 to get 4 is equal to 2a. And let's substitute y is equal to -2 to get 2 is equal to -2b. So a is equal to 2 and b is equal to -1. So this is 1/3 through 1 of 2 over y minus 1 over y plus 2. To make sure that this is giving us y plus 4 after we combine the fractions. Looks good. So after integrate, it's going to be 2 times ln of y minus ln of y plus 2. 1/3 through 1. So after plugging in 1, 2 times ln of 1 minus ln of 3. Plugging in 1/3, it's going to be 2 ln of 1/3 minus ln of 7/3. ln of 1 is equal to 0, so this is going to be negative ln 3. This is same thing as ln of 1/9 minus ln of 7/3 by putting 2 into here. Let's simplify this a little bit. So this is going to be ln of 1/9 plus ln of 7/3 and make it to single ln. So it's going to be ln of 1/3 times 9 times 7/3. So it's going to be ln of 7. So it's going to be ln of 7. Okay, number 2. So it's an integral of x squared plus 64 1 dx, where x is ranging from 8 over square root of 3 through infinity. So this is a program, you have a sum of the squares. So it's kind of using a trigonometric substitution. If you remember the formula, just use the formula. If you don't, then you have to set up the trig substitution like this. So first of all, this is an improper integral of type 1. So let's make it to 8 over square root of 3 through b and make b goes to infinity. Let's make a substitution here. So let x over 8 is equal to tangent theta. So x is equal to 8 tangent theta. Dx will be 8 times secant square theta. X is ranging from 8 over square root of 3 through b. So the corresponding value of theta will be, so tangent will become 1 over square root of 3, so it's going to be pi over 6. And here it's going to be inverse tangent of b over 8. After making a substitution, this will become pi over 6 through inverse tangent of p over 8. And x squared plus 64 is going to be 64 tangent square plus 64. And the dx will become 8 secant square theta d theta. D theta here. Now this part will become 64 times tangent square plus 1, which will become 64 times secant square. So this is going to be 8 secant square theta over 64 times secant square theta, d theta. So that's going to be 1 over 8. So after integrating it, you want to get 1 over 8 theta, and you want to plug in these values. Limit. So the first one will give us 1/8 inverse tangent of b over 8 minus 1/8 times pi over 6. Okay, if you remember the formula for 1 over x squared plus a squared dx, then just use a formula, then you can bring it to here in just one step, basically 1 or 2 steps. Now you plug in infinity here, so you are considering about that inverse tangent of infinity, and that is corresponding to pi over 2. Okay, pi over 2. So it's going to be pi over 2 minus pi over 48, which will be 3 pi over 48 and pi over 48. So it's going to be pi over 24. It's going to be pi over 24. Okay, that was a long question because I didn't remember the formula. I recommend you to memorize the formula for this. So that's going to save lots of time. Okay, number 3. 0 through 16 of dx over square root of 16 minus x. Now, the square root of function is very defined between 0 through 16. However, this is in the denominator. So this is not continuous, not well defined at x is equal to 16. So the graph exists between 0 through 16, but not existing at 16. So the graph is at x is equal to 16. You want to have something like this. So this is a type 2 improper integral. So we have to set like 0 through b of the integral. And we are going to make b approaching 16 from left side. Now the integral of this one will be 16 minus x. This is power of -1/2. So using power rule, after integrate, you're gonna get 1/2 here and divided by its reciprocal and divided by the derivative of the inside, which is -1. Now plug in b, it's gonna be -2 times 16 over b square root plus 2 times 16 square root. Okay. Now make limit. 取りま代入して、-2 square root of 0 plus 2 times 4, which is 8. So the limit exists and the limit is equal to 8. Okay, next one. Number 4. negative 27 through 64 of x to the power of 1/3, 1 dx. So this one looks like a normal integral, but remember that this is not defined at x is equal to 0. So the graph has a vertical asymptote at x is equal to 0. So something like this. So we cannot integrate negative 27 through 64 directly because function is not continuous. It has a value into this part and this part. So first thing to do is rewrite this one as negative 27 through 0 plus 0 through 64. Both of them are improper integrals, so we are going to use the limit approach. So limit c approaches 0 from left side for the first integral. So negative 27 to c of x to the power of negative 1/3. And on the right side, it's going to be c through 64, where c approaches 0 from right side. This is just a power function. So using a power rule, add the power by 1 and multiply it by, or divided by itself, or multiplied by its reciprocal, it's going to be 3/2. And you plug in like this. Okay, and do the same thing here. Basically, same function, just plug in different value here. So for the first one, it's going to be 3/2 c to the power of 2/3 minus 3/2 times negative 27 to the power of 2/3. Second one is 3/2 64 to the power of 2/3 minus 3/2 c to the power of 2/3. And plug in 0, 0 to the power of 2/3 will be 0. So it's going to be 0 minus 3/2 times, this is going to be negative 3 times negative 3 squared, which is 9. And this is going to be 3/2 times 4, 16. And 0 to the power of 2/3 will become 0. So the answer will be 16 minus 9 times 3/2, which is 21/2. So the answer is 21/2. Okay, number 5. Negative infinity to 5 dx over x squared plus 25. This 5 is not really matter, but so this integral is basically like in the previous question, this is the integral of this one. So if we go back both for using a formula, we can integrate it in an instant. So the formula says 1/8 inverse tangent of x over 8. So that's kind of formula. So this is actually equal to 1/a inverse tangent x over a plus c. So let's use this formula this time to save time. Okay, so here, improper integral of type 1. This is well defined everywhere because denominator will never become 0. So this is just a type 1 improper. So let's say it's going to be a through 5 of this integral, where a is approaching negative infinity. Using a formula to find the antiderivative, it's going to be 5 times 1/5 inverse tangent x over 5, a through 5. that is equal to, this is gone, and it's going to be inverse tangent of 1 minus inverse tangent of a over 5. So inverse tangent of 1 is, so the tangent become 1 at the pi over 4 degree radian, and the plug in negative infinity here, so tangent become negative infinity at negative pi over 2. So it's gonna be, the limit is like this. So the answer is 3 pi over 4. 3 pi over 4. Okay, number 6. So number 6 is actually negative infinity through infinity of 2x over x squared plus 1 to the power of 9. So this one has a two-side improper. So let's split into two pieces. So it's going to be, this is well defined inside everywhere. Yeah, the domain is every real number. So there's no vertical asymptotes in between. So let's consider this is integral of a through c and c through b, and just a make it to negative infinity and b make it to infinity. And c can be any number. So let's just pick 0 for simplicity. So split into two pieces, a through 0 and 0 through b. Like this. Okay. Now integral this one is very simple. It's going to be x squared plus 1 to the power of negative 8 and divided by negative 8. It's like if you are not comfortable with, you have to use a substitution. But basically, if you say this is u, you can find the integral quickly because derivative of the inside is here. So it's going to be a through 0 and the same function here, and 0 through b. So plug in 0, it's going to be 1. So it's going to be negative 1 over 8 plus 1 over 8 times a squared plus 1 to the power of 8 here. I'm doing here same thing. It's going to be negative 1 over 8 b squared plus 1 to the power of 8 plus 1 over 8. Now taking the limit here, it's going to be infinity in the denominator. This is 1 over infinity, so it's going to be 0. And this is going to be 1 over infinity, so it's going to be 0. So it's going to become negative 1 over 8 plus 1 over 8. So the answer will become 0. Number 7. So again, this function is not defined, not continuous at theta is equal to 0. So we have to say a through 7, where a approaches 0 from positive direction. Okay, so let's just do the indefinite integral first to see what this become. So if you are not seeing it clearly, but you see that the inside the derivative is here. So when you say u is equal to theta squared plus 3 theta, then this is going to become square root of u du, whose integral will be 2 square root of u plus c. So after the integral, it's going to become 2 times square root of u, which is this. And you want to plug in 7 and a. You can plug in a 0 immediately. So it's going to be 2 times square root of 49 plus 21 minus 2 times square root of a squared plus 3a. But after making a approaching 0, 取りま代入. So it's going to be 2 square root of 70. Number 8. 0 through infinity of dx over 4 plus x times square root of x. Okay. So the problem states that this integral will converges to some number, and we need to find what it is. This is kind of a complicated expression. It is not defined at 0, and this is also an infinity, so we have to use a limit eventually. But let's do the just the indefinite integral part. So this is equal to, let's say u is equal to square root of x. So u squared is equal to x. So 2u du is equal to dx. So after making a substitution, 2dx become 2u du, x become u squared, and root x become u. After reduce the fraction, this is like a arctangent pattern. So using a formula which we checked previously, it's going to be 1 over 2 arctangent of u over 2 plus c. We don't care about plus c because we are going to do the definite integral later. So this is inverse tangent of u over 2, and u is square root of x. So this is going to be the antiderivative of this function. So keep this in mind. We write this expression as limit a approaches 0 from positive direction of a through, who cares? It could be anything between 0 through infinity. So it's a 1, just say 1. It can be any number between 0 through infinity. And this is going to be 1 through b, where b goes to infinity. Now, using the antiderivative we just derived, so this is going to become inverse tangent of square root of x over 2. Maybe I should make it 4 here instead of 1 because it looks nicer. So I'm just going to change to 4. Yeah, I mean, just split 0 to infinity at anywhere you want. So I just split at 4. Yeah, that looks nicer. Should be. So this is going to be, when you plug in 4, it's going to become arctangent of 1. So it's going to be pi over 4. Remember, tangent become 1 at 45 degrees. So pi over 4 minus arctangent of square root of a over 2 plus arctangent of square root of b over 2 minus pi over 4. Now you take a limit a approaches 0, and you take a limit b approaches infinity. So it's going to be pi over 4 minus inverse tangent of 0 plus inverse tangent of kind of goes to infinity minus pi over 4. So tangent becomes 0 at 0 degree, and tangent becomes infinity at 90 degree. Yeah, when you take a limit, so it's going to become pi over 4 minus 0 plus pi over 2 minus pi over 4. And that is equal to pi over 2. So the answer is pi over 2. Okay, number 9. Let's look at the expression. This is a continuous function everywhere. So it is, again, a type 1 indefinite integral. So we just take a limit later. So just put, say, a here. This integral is a typical integral using integration by part. So the exponent this side and the linear function here. So it's going to be 1, 0, and e to the theta, e to the theta. Using the table, this becomes theta e to the theta minus e to the theta, a through negative 3. And you're going to take a limit later. So that's going to become negative 3 e to the negative 3 minus e to the negative 3 minus a e to the a minus e to the a. Now we are going to take a limit of this one. So what is the limit of, this is just a number, so this is done. And the limit of this one will be, you want to consider e to the negative infinity. Okay, we are going to take a limit a approaches negative infinity. So we are going to think about this, but this is equal to 0, as you see in the graph of y is equal to e to the x. This one is a harder one because this is going to become negative infinity times e to the negative infinity, which means infinity times 0, which is indeterminate form. 不定形ですね。不定形。So that's kind of harder to evaluate. So let's use a L'Hopital. So the hard part of this problem is this. And you can rewrite this one as a times e to the power of negative a. So in that case, you see this kind of numerator become negative infinity, denominator become e to the infinity, which means infinity. So this is an infinity over infinity format. So we can use a L'Hopital. Using a L'Hopital, take a derivative of the numerator, take a derivative of the denominator, and you are going to plug in again. Then you want to get the limit. So that's gonna be 1 over negative infinity, so that's going to be 0. So this, the limit of this one is equal to 0. So this approaches 0, and this also approaches 0. So the final answer is this, which is e cubed on the bottom, negative 3 minus 1. So it's going to be negative 4 over e cubed. Okay, number 10. So it's negative infinity through infinity of 10x e to the minus x squared dx. So again, let's say this part is u, and let's take a definite integral first, indefinite integral first. So actually, you can say u is equal to negative x squared. So du is negative 2x dx, which is basically here. So after making a substitution, it's going to be e to the u, and this piece will become negative 5 du. So after the integral, it's going to be this plus c, and that's going to be negative 5 e to the minus x squared. Since this is an improper one, we had to split it into a through 0 plus 0 through b, and we are going to take a limit later. Okay, we're going to take a limit later. So this is going to be negative 5 e to the minus x squared, a through 0. And this is negative 5 e to the negative x squared, 0 through b. Plugging 0, it's going to be negative 5. Plugging a, it's going to be 5 minus 5 e to the power of minus a squared. you're going to take a limit. Same thing here, plug in b, -5 is minus b squared, minus plug in. Now taking the limit, it's going to be -5 plus 5 e to the negative infinity, plus -5 e to the negative infinity, plus 5. E to the negative infinity, e to the x is like this. So e to the negative infinity is approaching 0. It's going to be 0, this is going to be 0. So the answer will be 0. Okay, number 11. Integral of -18 through 2 of 1 over square root of absolute value of 2x dx. Well, clearly this function is not defined at x is equal to 0 because the denominator becomes 0. So this is an improper integral of type 2. So let's split this one into -18 through 0 plus 0 through 2. When x is 0 through 2, the inside absolute value is positive, so you can remove the absolute value sign. And when x is between -18 through 0, the inside absolute value is always negative, so you can remove the absolute value sign like this. Okay. Now let's say this is a, and this is b, or whatever, and you take a limit a approaches 0, and you make say b approaches 0. So after the integral, it's gonna be square root of -2x minus, and even minus this, yeah, -18 through a limit, and the limit, same function, square root of 2x, b through 2. So this is gonna be minus 2a square root plus square root of 36 plus limit b approaches 0 plus of 2 square root of 2 times 2 minus square root of 2b. And you can torimadai new. So it's going to be 0 plus 6 plus 2 minus 0, which is 8. Okay. From here, the program changes, and it is asking about whether the function, whether the integral is converging or diverging. So now let's look at this expression. So this is integral of tangent 6 theta d theta, where theta is from 0 through pi over 12. Okay, so what is the integral of the, well, this function is undefined at pi over 12 because when you plug in here, the inside the tangent becomes 90 degrees, and tangent is not defined at 90 degrees. So we have to use the limit b approaches pi over 12 from left side of this function. Remember, tangent function is undefined at pi over 2. And when you plug in this one here, you want to get pi over 2. Integral of the tangent is good to memorize. So it's going to be negative ln of absolute value of cosine 6 theta. And you have to divide it by 6 by the chain rule. Plug in b, it's going to be -1 over 6 ln cosine of 6 times b plus 1 over 6 ln of cosine 0. Cosine 0 is equal to 1. Ln of 1 is equal to 0, so this is gone. And you want to take a limit. So it's going to be -1/6 ln of absolute value of cosine pi over 2 from left side. So as cosine, the angle approaches 0 from left side of the cosine function. So think about the cosine function. So y is cosine function. So x is approaching 0, pi over 2 from left side. So inside of the ln is approaching 0 from positive direction. Okay. So this is a limit of the log now. So now we are going to consider the log. So y is equal to ln x is a base function. And as x approaches 0 plus, so as x approaches 0 plus, y value is getting negative infinity. Okay, look at the basic log function. So the limit will be infinity over 6, which is equal to infinity. So the answer is infinity. And that means this is diverging. Okay. Now, next one is a very complicated expression. Square root of t and sine 2t is involved, and that's kind of too complicated. So let's going to use a comparison test because this is kind of too hard to integrate. So something similar to this function is this. This is something easy to integrate, and this is something similar to this. Okay. Now, when you integrate this one, you have to take a limit later, but it's gonna be 2 over 11 square root of 11t. And you just plug in pi over 2 through 0, a, and a approaches 0. So that's gonna become some finite number like this, minus 0. So this one really converges, this converges. Now, we know that this converges. How can we show that this converges as well? One idea is just like try to show that this integral must be smaller than this, but greater than something else. So what we do, when t is between 0 through pi over 2, 2t is greater than 0 and less than pi. So the angle inside the sine function is between first quadrant and second quadrant. So sine of 2t must be non-negative. Okay. So this means that this denominator is at least as big as this one. So square root of 11t plus sine 2t is at least is equal to this. Okay. So when, we don't want to put t equal to 0 because the denominator becomes 0. But when t is greater than 0, or when t is greater than a, so when t is greater than or equal to a, which is greater than 0, then this is all positive. So its reciprocal exists, and the reciprocal, this flips. The greater the denominator, the smaller the fraction become. So when you graph those two functions, let's say this is f and this is g. Then the f is always greater than g. Okay, f is always greater than g. So if f has a finite value of the area like this, then area defined by this should be smaller. So this should have some finite number. So we can say this one will converge to something. And this should be greater than 0. Yeah. So since 1 over square root of 11t plus sine 2t is always less than or equal to 1 over square root of 11t and always greater than 0 or greater than or equal to 0, we can say that the integral of this one is less than or equal to integral of this. And that is less than or equal to integral of this. And this one has some number, this, some number. I don't know what it is, but it is just some finite number. That's all we care about. And this one is clearly 0. So this one, we don't know how to find the value, but it is bounded below by 0 and bounded above by some number. So it means this integral converges. Okay. Okay, so next one is use integration, direct comparison test, or limit comparison test to test the integral for convergence. If there is more than one method applies, then just use whatever method you prefer. So this one, you cannot integrate directly because this one is undefined at x is equal to 4. 4, that the denominator becomes 0, right? And negative 4. Since the interval here is 0 through 8, we have to split the integral at 4. Okay, now when x is greater than 4, it's going to be negative. When x is less than 4, it's and because of negative 4, it's going to be positive. So we had to consider g's part. Now, so this is going to become limit a approaches, no, b approaches 4 minus of 0 through b plus the limit of a approaches 4 from right side of the 4 through, a through 8. Yeah, we have to split into 2 pieces. Now, how do we integrate this? This one, you can factor into 2 different linear terms. So you can use partial decomposition. And after you do that, it's going to be 4 minus x plus 1 over 4 plus x divided by 8. So that's going to be after you do the partial fractions. Let's just focus on left side, the first term, because this one, we can do it similarly later. And I'm going to show that this going to diverges. So after integrating this, it will become negative 1 over 8 of ln absolute value 4 minus x plus 1 over 8 ln absolute value 4 plus x. And you plug in 0 and b. So that's going to be here's the limit. 4 minus. So you plug in b, it's going to be 4 minus b plus 1 over 8 ln 4 plus b. And when you plug in 0, it's going to be negative 8 ln 4 plus 1 over 8 ln 4. So that's gone. You can do similarly here. But when you take this limit, it's going to be negative 8 ln of 0 plus 1 over 8 ln 8. What is this? Y is equal to ln x, and the inside becomes 0 from the right direction. So it's going to be negative infinity. So this is going to be negative 1 over 8 times negative infinity plus some finite number. So this limit is equal to infinity. So the first part will become infinity. So this part will become infinity. So it is actually diverging. So you really cannot find a finite solution to this integral. You don't need to do this part because in order to have this to be converging, we need to have this limit to be convergent. and this limit to be convergent as well. Since this is diverging, the entire integral must be diverging. Okay, next one is, yeah, again, it's like checking whether this has a finite number or not. Well, this is clearly even function. So it's a ln of x, but because it's even function, it's gonna be looks like this. So basically, if it is converging in this part, then it must be converging this part. If this is diverging in this part, this must be diverging in this part as well. This function is not defined at x equal to 0, so it's natural to split this one into -9 through 0 and 0 through 9. However, we just need to evaluate right-hand side to see whether it's convergent or divergent. So let's consider 0 through 9 of ln of absolute value of x and times 2. I mean, hoping this converges. So when x is positive, we don't need absolute value. So it's 2 times limit a approaches 0 from positive direction of a through 9 of ln of x. We removed absolute value sign because we are only working with a positive value of x's in this interval. The integral of log x is a typical example of the one using a partial, not a partial, integration by part. So put ln x here and make it its 1 times and use a integration by parts technique. So it's going to be this times this minus integral of this times this, which is x. So after you do something, it's going to be x times ln x minus integral of 1 over x times x dx, and that is equal to x ln x minus integral of 1, which is become x. And it's good to memorize the integral of ln x because we're going to use it quite frequently. So after the integral, it's going to be x ln x minus x, and you plug in a and 9. So it's going to be 9 ln 9 minus 9 minus a ln a minus a. Now you have to take a limit. And the limit of a is converging to 0, so that's good. But the limit of this one is kind of hard to do, so let's do this one separately. So what is the limit of this? A times ln a. Torimadai-nyu, when you just Torimadai-nyu, it's going to be 0 times ln of 0 plus. And ln of 0 plus is, again, it's going to be negative infinity. So it's going to be 0 times negative infinity, which is indeterminate form, 不定形. So we have to deal with this one somehow. And the idea to do this one is actually rewrite this expression as a fraction like this. So kind of divide top and bottom by a like this to make it a fraction. Then this become infinity, infinity format. So you can use a L'Hopital. Using a L'Hopital rule, this is going to become 1 over a over negative 1 over a squared, which is really equal to negative a. So the limit is equal to 0. So fortunately, this becomes 0 and this becomes 0. So the limit is 2 times 9 ln 9 minus 9. Okay. So looking at the choices, choice D said the integral has a finite value, so the integral converges. Okay. So C is clearly false because it said integral does not have a finite value. Okay. So this one, we don't know what this compares to, but the conclusion is wrong because it said integral diverges. Okay. So this said using some comparison. the integral converges. The conclusion here is correct, but it doesn't make sense because it's using a totally different domain. So domain is totally different from this one. So it doesn't make sense why this means that in this interval it's converging. まあだから、マイナス9からマイナス無限でコンバージするから、マイナス9から9などでコンバージするみたいなこと言ってるわけですけど、まあ範囲が違うので、当然結果は全然関係なくてですね、これはもう意味がわからないと。ここの結論だけは正しいんだけども、理由は全然正しくないので、まあ、this is not the correct choice. Okay, number 16. So this one is asking for performer test to determine whether this is converging or diverging. So this is just a multiple choice. So if you try one and failed, then another one must be correct. So let's do the antiderivative first, because inside derivative is, well, not actually inside derivative is not here. Well, we might want to do some kind of technique to integrate. So let's see. So the numerator is basically x to the power of 4.5. It's kind of close to this. So this integral is basically something like this. So we can compare this one with a P-series test, okay? So x to the 9 plus 6 is less than or equal to x to the power of 10 plus 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 x to the power of 10, or anything. Well, if you can just say anything, it's less than 9 times x to the power of 10 when x is greater than or equal to 1. So for all x greater than 1, x to the 9 plus 6 is less than or equal to 9 times x to the power of 10. So when you take a square root, this is also true. And this is equal to 3 times x to the 5. What we want to do is a comparison. So we are going to compare this function to 0 and compare it with this function, because this is easy to integrate. Okay, now this integral is equal to 1 through infinity of 3 over x to the minus 3. So it's going to be 3 times x to the minus 2 divided by minus 2, and you're going to plug in 1 through b goes to infinity. So that's going to be 3 over negative 2 infinity plus 3 over 2. So it is converging. Well, if you remember what we have covered in the class, that x to the p, 1 over x to the p, 1 through infinity converges if p is greater than 1. So this is a case that the p equal to 3. I mean, sorry, it's 3 here. 3 here. 3 here, so it's going to converge. So since this has a finite value when you integrate 1 through infinity, then this one must also have a finite value when you integrate this complicated integral 1 through infinity. So by direct comparison test, this integral converges. Okay. Okay, next one. This is also a complicated one because you have cosine divided by the quadratic. Okay, that's really complicated. So you are going to compare this one with something which is easy to integrate. And remember, for any x in real number, cosine of whatever is between -1 and +1. So adding 9 to this is between 0 and 8. Divide everything by x squared doesn't change the order of the numbers when you have x is positive. So this is clearly a positive value when you integrate it. And we want to show that it is not going to infinity. And yeah, so this goes to finite value by P series with P is equal to 2. And this is also P series with P equal to 2. So this converges and this converges. So the inside of this one should converge to something. So when you integrate this one, 10 over x squared dx from some number to infinity, it's going to be -10 over x, infinity to pi over 5, and that's going to be 0 plus 10 over pi over 5, which is 50 over pi. So this has some finite value. And this one should be less than this number, but it must be positive. So, so the graph is like something like this. So the area is keep increasing as the interval is getting to infinity, but it is bounded above by 50 over pi, so it must converge to some number. We don't know what number that is, but we can say this limit, this integral will converges. Okay, next one is another one that it seems to be difficult to integrate. 2 through infinity 5 over square root of e to the power of x minus x dx. So when the x is getting large, very large, then we have to know what is the dominant, what is has a dominant power. So e to the power of x is actually much greater than x. Remember, when you have an exponential function, trig function, polynomial and log, forget about the trig for a moment. This usually have a dominant power compared to those. So this one is usually stronger, and this one is weaker. So when x is big, e to the x is very, very big, and x is very, very small compared to e to the power of x. So when x is large, square root of e to the power of x minus x is kinda almost equal to this, and that is equal to e to the power of x over 2. And that means this function can be compared with this. This is easy to integrate because it's just like exponential function. And so it's going to be -10 e to the power of e like this. And infinity and 2. So it's going to be -10 e to the negative infinity plus 10 e to the power of -1. And this is equal to 0. So it's going to be converging. It's going to be converging. Now, how do we show that this really converges? So we know that approximately this is equal to this and this converges. How do we show that this really converges? Well, in this case, you can say for any x greater than or equal to 2, e to the x minus x is clearly smaller than e to the x minus 0. And when x is greater than 2, this is greater than 0. So this is greater than 0, and this is smaller than this. Okay, so the denominator is actually, this one is smaller than this. So since these are positive, when you take a reciprocal, it's going to be something like this. And that's not really good. That's not really good because we showed this is converging. but this is greater than that. So we are not really sure that this converges. Okay, that's something we don't want. Yeah, we don't want something greater. So this comparison is not really working well. So we had to make some kind of adjustment. So one way to adjust is like try to find something. We can make some adjustment to make something that is easy to integrate, but smaller than this. Smaller than this. So what we can come up with, one thing we can use is like maybe just divide this one by 2 or 3 or something. So e to the x minus x is, we wanted that to be greater than something that can be easy to integrate. Okay. And one way to do is maybe e to the power of x. Yeah, it's kind of not so easy to explain. let me think about this. Yeah, I'm gonna pause this. Okay, so the direct comparison is not really effective in this case because this minus x is not easy to compare with. But so let's use a ratio test. So which state if the limit of one of the function with another function, which is 5 over square root of e to the x. If the limit is finite, then if this is finite, then that means both diverges or both converges. で、まあ、上と下のね、比率が、x 無限にするときの比率が有限になるならば、両方ともダイバージ、または両方ともコンバージ。つまり、コンバージするか否か、両方とも同じですよっていうことなんですね。片方だけコンバージにはならないよってことです。So, we are going to show the limit of this ratio is finite. So this is going to become square root of e to the power of x over square root of e to the power of x minus x. So this is the limit of infinity over infinity type. So let's divide top and bottom by the largest factor, which is square root of e to the x. So it's going to be 1 minus x over e to the power of x. Okay. Now taking the limit, as x approaches infinity, denominator is much bigger, but if you want to do it rigorously, this is infinity over infinity type indeterminate form. So you are going to use the L'Hopital derivative top, derivative bottom, and plug in again, it's going to be 1 over infinity, which is 0. So this is going to become 1, which is a finite. So since this is finite, it is finite value. And one of the limit to through infinity of this one converges. So is another one is also converges as well. Okay. これが有限ってことは、まあ、この2つはその面積の広がり方としては同じレベルなので、まあ、片方が有限になるんだったらもう片方も有限になるし、まあ、片方が無限になるんだったらもう片方も無限になりますっていうことです。So, we just show they are comparable, they have a same convergence, and we just show one of them converges clearly. So, the problem in our hand is also converging. Okay, number 19. Find the value for p for which the integral converges. So 1 through 2 of dx over x ln x to the power of p. Okay. Now, first of all, we want to integrate this one. But remember, ln of 1 is 0. So we have to use a limit as a approaches 1 from right side of a through 2. Let's use the integration by parts. Or maybe actually substitution. Because the derivative of ln is actually written here. So let's do the integral first. Okay. So let's say u is equal to ln x. Then du will be 1 over x dx. So after making a substitution, it's going to be 1 over u to the power of p du. Okay. So this becomes 1 over u to the power of p to the du. And actually the value we're going to have is when x is 2 and well, basically it's 1. So 2 and 1 is equal to, when x is 2, it's going to be ln 2. And when x is equal to 1, the u become 0. It's going to be 0 through ln of 2. So this is 0 through ln of 2 of 1 over u to the power of t du. Okay, so this integral is like you have to split into cases because when p is equal to 1, it's kind of special. So when p is equal to 1, it is the integral of 0 through ln of 2 of 1 over u du. That is equal to ln of the absolute value of u 0 through ln of 2. Okay, where 0 is basically you have to take a limit actually. But it's going to be ln of 2 minus ln of a, where a goes to negative, a goes to 0. So this is going to be negative infinity. Remember, ln become negative infinity when input becomes 0 from right side. So it is diverging at p is equal to 1. When p is greater than 1, this integral will become u to the power of a negative p plus 1 over 1 minus p. And that is equal to, because p is greater than 1, it looks like this. And when you plug in 0 here, it's going to be like approaching 1 over 0 plus. So it's going to be like infinity, negative infinity. This one is okay, but this going to give us negative infinity. So when p is greater than 1, it diverges as well. Diverges. When p is less than 1, same integral, so it's going to be like this. But this is positive now. This is positive now, so it's not on the denominator, but it's actually on the numerator. So the limit does exist. And that is equal to some number like this. So for what value of p, it converges. So it converges for p is less than or equal to, or less than 1. Okay. Now, but if you do something similar for the different interval, which I'm not going to show it here, but in this case, it's going to be kind of switched. So when p is greater than 1, because now instead of plugging 0 through ln 2, you want to plug in ln 2 through infinity. So now this is going to converge. If you plug in 2 through ln of 2 through infinity, then this is going to diverges as well. And this is going to be diverges as well, because this is going to become infinity. So it's going to just switch P is greater than 1, less than 1. So this is going to be the convergence. Yeah. Oh, what is it? Yeah. Okay. Now number 20 is so you have some integral like this, which is sine t over t, where 0 through x. We cannot integrate this one using the symbols we have learned so far. So there's some symbol given here. So this is called sine integral function. And let's answer the questions. So plot this one. So we have to use a calculator. This is a calculator involved question as it's t state here. So plot this one using a function and to show that it's increasing or decreasing. And it is, yeah, you have to use a calculator to find which one looks correct. And it's actually turned out to be A. And is it increasing everywhere, decreasing everywhere? And it's really not, because it has increasing, decreasing, increasing, decreasing, increasing, decreasing, and so on. So is a function everywhere increasing or decreasing? The answer is no. Okay. So does the function become 0 for x is greater than 0? This is kind of hard to say, but actually it will never become 0. And here's quick explanation. So this is sine. When you plot this one, it start with like something like this. I mean, this graph looks like this, and so it's like a sine wave, but bounded above by y is equal to 1 over x, and bounded below by y is equal to negative 1 over x. Now, area here is positive. So when you start integrating this one, it starts with positive. But then you are going to have a negative area. So it's going to be decreasing. So when you integrate it, you start with positive, 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 and it's starting to decrease the value. However, because the green is greater than blue, when you integrate from here to here, the result will be positive. Result will be positive. Then you want to have more area, more positive area to be added, and a smaller area to be subtracted. So when you integrate from 0 through x, for anywhere you stop, the total on the positive side is greater than the total in negative side. So for any value of x, the result of the integral must be positive, must be greater than 0, because green is always greater than blue. So does this function become 0 for any value of x? The answer is no. Now, explore the convergence of this one. So now we have to use some kind of technique to show this is converging or diverging. And it's kind of difficult to say, but this one is actually converging because it's kind of alternating the values of positive and minuses. And because this alternation is getting smaller and smaller, so there's some alternating series convergence test, but I'm not going to explain that one in this section. But just say that this is converging right now, okay? だからまあ、プラスマイナスって続く数列があって、この数列の値がだんだん0に近づく場合は、それらを全部足したものも、まあ、何らかにコンバージするよっていうのを保証してくれる定理があるんですね。まあ、それをまあ使うことになるんですけど、まあ、その証明はちょっとここではできませんので、まあ、それを使ってくださいとしか言えないです。はい。Now, the last question is kind of tough. Yeah, explore the convergence of this integral. So we really cannot integrate this one by hand. So try to use a calculator to see what this value really approaching to. So you can just say 0 through big number, sine t over t, and try to see what that number really is. Okay, so you really need a calculator to see, guess what this value is really equal to. That's complete explanation for this section.